Alright, so in the last few videos we were talking about the RNN, how the RNN architecture looks like, the different equations that are involved in the RNN architecture, and how also I described how if we take the derivative of the error with respect to the weights, how RNN suffers a problem of vanishing gradient, right? So the derivative with respect to the weights we generally call as back propagation through time, because we are kind of calculating the gradients at each time stamp and then we are doing a back propagation, right? So with that, let's try to understand how LSTM works and what is the architecture of LSTM and how it can solve the vanishing gradient problem which we have seen in case of RNN. Okay, so now let's get started. So first of all, if I just look into the architecture of LSTM, it has certain inputs which are like xt and ht minus 1. It also has a new thing which got introduced in LSTM, that is a cell state, and also it outputs ht, right, which is nothing but the hidden state. So the new thing which got introduced in case of LSTM is the cell state. So actually this cell state is kind of responsible for tackling the vanishing gradient problem, which is associated with the long-term dependencies in case of RNN. Right now, there are also certain gates which are new to LSTM, and all these gates generally update or control the cell state. Right, so the gates are like forget gate, input gate, and output gate. So these three gates are mainly responsible for updating or controlling the values of your cell state. Right, now let's first talk about the forget gate. So the forget gate generally works the given the new information. The forget gate controls what information in the cell state to forget, right? So if I just write down the equation, this is the equation where we have a sigmoid activation function. So this is nothing but a sigmoid activation function, then the weights associated with the forget gate, and we have the two inputs which are like ht minus 1 and the current input which is xt. So these are like my inputs and this is the weights, and after taking the sigmoid activation function we get the forget state output, right, which is nothing but ft. So as it uses a sigmoid activation function, so it will the output will always be in the range of 0 to 1. So whenever the value is closer to 0 or 0, that means let nothing through, right? So it will like forget the things which are there in the cell state, right? And whenever the output is 1, that means let everything go through of cell state, right? So if I just take an example, right? So uh, if this is my the output of ft, right? So if my output of ft is like this, 0 0 0 1 1 1 0 0, then again 0 1, something like this. And if you can see, we are doing a element wise multiplication with cell state here, right? So if my cell state, which is nothing but this, it will also have a similar shape, because we are doing a element wise multiplication, so this ft and ct has to be of the same shape, right? So we have certain values like 2.5, then 001, and all this like another few values. So whenever we multiply these two things, right, so whenever it is 0, whenever the places where the forget gate value is 0, so that values will be eliminated, right? So this will become 0, this will also become 0, because the first three element itself is 0, right? So you can understand like whatever the value that is coming from the previous cell state, which is nothing but ct minus 1. So this actually it was ct minus 1. So once we multiply this ft and we do element wise multiplication with fct minus 1, so certain parts of my previous cell state will be forgotten, and whenever there is the forget gate value is equals to 1, so that will be remembered and used in the further process of my LSTM, right? So I hope you got an understanding with this, like what is the job of forget gate. Now let's come to what is input gate, right? So in case of input gate, what we are doing is in the input gate decides what information will be added to the ct, right? So in case of forget get, we were kind of eliminating few of the informations from the previous cell state, but using the input get, we will decide what new information will be added back to the CT, right? So if you just look at the math or the equations, it has actually two sections. So this is the weights associated with this part, and also we have a weights which is like WI, WC and WI. So with the help of WC, we take tan H activation function, and we get this CT dash. So this part will be CT dash, which is nothing but this equation, which is tan H activation function, then weight multiplied with the inputs, which is HT minus 1 and XT, right? And we also get this IT. So IT is nothing but the sigmoid activation function, and then we are multiplying weights with the inputs, which are like HT minus 1 and XT, right? And after that, we are kind of doing a element wise multiplication, right? So this output will be my input gets output, which is nothing but C tilde element wise multiplicated with IT, right? So that will be the output of the input gate. And again, if you see here, we are using the sigmoid activation function here, and then we are doing element wise multiplication, right? So whenever we are using a sigmoid activation function, the output will be always in the range of 0 to 1. And after that, if we are doing a element wise multiplication with any other input, so some parts will be zeroed out and some part will be kept as it is. So zeroed out when the sigmoid activation function's output is equals to 0, and will be kept as it is when the sigmoid activation function's values are equals to 1, right? So once that is done, then we will add back this information to the FT, right? So this path is nothing but FT multiplied element wise multiplicated with CT minus 1. So after that, we will get the updated CT value, right? So this is after doing this addition. So if you see, we will update CT minus 1 to the new candidate or new candidate cell state value, which is CT. So FT will be multiplied with element wise multiplication with CT minus 1, which is the operations during the forget gate, and this is the input which is coming from the input gate, right? And we finally get the updated value of CT, right? So with this, we are kind of forgetting few parts of my previous cell state using the forget gate, and we are adding few things using the input gate, right? And we get the new updated cell state value, which is CT, right? So after that, the last gate which is there is output gate, right? So the output gate decide what information encoded in the cell state will be propagated as HT. HT is nothing but the input for the next timestamp, right? So if you see, like at first it calculates the output gate output, which is OT. So the OT will be calculated using this sigmoid activation function. So your WO is the weights associated with output gate. So WO will be multiplied with the inputs, which are like HT minus 1 and XT, and then we use a sigmoid activation function, and that will be element wise multiplicated with the tan H of CT, right? So here again we see that this OT is nothing but will be the output in the range of 0 to 1, right? So it will decide what information from the CT, right? So CT is we are using a tan H activation function on top of CT, and then we are multiplying with the OT, right? So OT is the sigmoid activation function we have used. So this output gate will decide what values will be propagated as HT, right? So HT will act as an input to the next step. So this OT, which I have written here, so that will be if it is like we are using a sigmoid activation function, so some of the values will be 0 and some of the values will be 1, right? So in that way, this OT will look like, and whenever it is 1, so those informations from CT will be forward propagated as HT, and whenever it is 0, so those information will be removed from the CT. while calculating the HT, right? So I hope you got an understand that the output gate decides what information that is already available in the CT. So here this updated CT is coming here, and that will be multiplied with the 10H, and this is where we are getting the OT. So this will be element wise multiplicated, and we will get the final HT. So HT is nothing but your OT element wise multiplicated with 10H of CT, right? So the output gate will control what portion of cell state value will be given as an output as HT, right? So with this, we will now talk about how the backpropagation through time in LSTM works and how it can solve the vanishing gradient problem, which we have seen in case of RNN, right? So the output in LSTM incorporates the cell state, right? So that we have seen. So using the cell state value, we are calculating the HT, right? So once HT is calculated, we can compute gradients over T timestamps, and which we also did in case of RNN also, right? Now if I just consider the gradient of the error terms for some timestamp k, right? So it can be written as dek by dw, and that can be written as this, which is same as which we did in case of RNN also, right? So it has a product term which is dct divided by dct minus 1, right? Now if you remember, ct is nothing but this. Now if I take the derivative of with respect to del ct by with respect to del ct minus 1, then we can use the multiplicative rule, which is like this. If I just take, so it will look like u multiplied by dv by dx plus v du by dx, right? So this is the formula which we will use. So this is the derivative formula of the product term, and that we will use, and we will get this term, right? So, and we can see each of the term here is like in the summation form, right? And if we denote each of these terms with like a t, b t, c t, and dt, we can see this is the equation 2 which we are getting, and all these terms are additive in nature, right? Now we can put back 2 into the equation 1, and we can get the final equation for del ek by dw, right? So you can see, like in case of RNN, this term was a multiplicative term, right? But in case of LSTM, this is an additive term, right? Now how LSTM can solve the vanishing gradient problem? Because this term is additive in nature, so if all these values are very small, right? So if we sum that, it will not vanish in case of what we were seen in case of RNN. If we multiply small values, the values will become much more smaller. But in case of addition, it's not the case, so it will not have the problem of vanishing gradient. And also there is a presence of CT, which is the cell state, in the derivative term, right? So here we can see that we have a term of CT. Here also we can see a derivative term of CT. So all that is present in the derivative of LSTM, right? So that CT will decide which part of the long-term dependency it should forget, and which part of the long-term dependency it should remember, right? Using the different gates. So with that, it can pick up the crucial information from the long-term dependency, and it can keep the things which are required or which are essential, and throw out which are not essential, right? So with these two things, we can say that LSTM will work much better in case of long-term dependencies while compared with the RNN. The main reason is here the derivative term is additive in nature, but in case of RNN, the derivative term is multiplicative in nature, which has a very high chance of going into the vanishing gradient problem. right? And also the presence of CT, which will essentially remember the crucial part of the long-term dependencies and throw away the part which are not required, right? So yeah, so this is the one which I wanted to talk about in this video. So I hope you got an understanding of why how the LSTM works with different gates, and how the derivative of LSTM is much more simpler while comparing with the RNN, and how it can solve the vanishing gradient problem. So I hope you like this video. So in the next video I will talk about how we can implement NLP task using Pytorch LSTM module, and so that we will do a hands-on coding part, right? So if you haven't subscribed this channel, please subscribe. It takes a lot of effort and research to make this type of videos, so I need your support. Also please like and share this video with your friends. Thank you. See you in the next video.